screen, didn't I? Okay, so screenshot, my screenshot. We're off to a good start.
Yeah.
Yeah.
All right.
No, there's no. It's the cosine. The cosine.
All right, so here's our function. This is number 10 from the homework. Oh, there we go. I am recording. Thank you. Number 10. And we'll call, I guess, do we have to give it a name? Sure, we'll call it f of x. And we need to identify outer. It looks like we have a middle here and an inner. And sometimes you could have multiple middles, so you should label them in a different way. So if I knew x, the first thing I would do is calculate negative 8x to the 6th. Once I got that answer, what would happen next? The sine or the square? The sine would happen next. That's correct. So the sine is the middle function. And then the outer function is the square. And you could throw the negative 4 times on that. So just a side note on that. Anytime you see something like the sine squared of whatever, technically what that means is the sine of the angle squared. Okay, so this is just shorthand notation for squaring the whole thing. And we need to consider that. So just got it all. Come on, 2. All right, so now we start taking our derivative. Oh, the square goes there. Yeah. Thank you.
So is it sine also again?
Nope.
No.
This is the inner. So if I know what x is, the first thing I'm going to do is plug it in and get that number. And then whatever the answer to that is, I'm going to give it to the sine. Whatever the sine says the result is, then I finally square it. And the negative 4 is just hanging out. It's just attached to the outside. So you could either put it there or just write it in front and then go. So for sure, f prime of x is going to have a negative 4 times. Right? So maybe I'll ignore that it's there. Now I take the derivative of a square. So that's going to give me 2 times whatever squared. Okay, what goes inside the square? Oh shit, right. Drop that by 1. All right. So now what goes inside the square? Well, inside the square is the sine.
Oh, yeah. And that was the sine of negative 8x to the 6th.
Yeah, that's what goes inside. Now I move on to the middle function. Derivative of the middle function is just the cosine. Notice how I leave these blank up here, right? That's important. And what should the inner function have for its argument? The middle function, sorry. Yeah, whatever was there before, right? So that's just going to be that negative 8x to the 6th. And finally, I get to act by multiplying by the derivative of the inner. So negative 48x to the 5th. And I'm going to put that in parentheses to be careful. Now we just clean up this mess. So we got a bunch of things being multiplied. I have a negative times a negative. So the answer is going to be positive 4 times 2 times 48. Oh, I can't do that all that in my head. Oh, I can't do that all that in my head. Somebody help me out. What's 4 times 2 times 48? 384. So I'm going to get a positive 384. And then I guess we could write the x to the 5th next, sure. And then we just have the sine times the cosine, right? So let me just double check here what I've dealt with. I've dealt with that stuff. I've dealt with that stuff. Yeah. Yeah, so the next part is just careful accounting things. So I'm going to have times the sine of negative 8x to the 6th times the cosine of negative 8x to the 6th.
This is to use the chain rule twice. So
well, we did apply the chain rule twice. We applied the chain rule to the outer function, which gave us a middle function, outer function. Then we applied the chain rule to the inner middle. So that's the chain rule twice.
Okay.
Yeah.
I was overthinking it. I was trying to chain rule whatever we got.
Yeah, no, it's just that what they mean is that you have this sequence of events happening there. Yeah, so I can't get it much simpler than that. Question?
No, sorry, just
There's a bug flying around. Okay. All right, and then I trust you guys can carefully plug that in, so I don't need to take the time to do that right now. Save my notes.
I have a question.
Yes, sir.
So how is this used in like everyday life? How is the chain rule like applied
So,
in real life?
good question. The chain rule is basically involved anytime you have a sequence of events, really. So, examples of the chain rule. Actually, I'm going to postpone that answer, and here's why. Because we have a whole section on just that answer, chain rule in real life, in chapter 4, which is hidden from you, but it'll be available soon. Where is it? Related rates. Yeah, related rates are physical applications of the chain rule. Yeah, that's what the chain rule does. It's how to relate two things that are changing together. Two or more things that are changing together. Yeah. Oh, I got another cute example of real life chain rule. The bicycle chain rule. So you got this bicycle and it looks something like this. So there's my bicycle.
So artistic.
I know, look at that. Oh, I need another bar in there. Otherwise this thing's gonna fall apart. Okay, oops, wrong color. All right, now it matches. So then you got this guy on the bicycle who's pedaling. That's me. And as he pedals, he moves this chain ring right here, right?
Mhm.
Right, but he's got a pedal. That chain ring is connected to a chain which connects to the bottom chain ring.
Mhm.
And that chain ring right there is connected to the rim, which makes the whole bike go. Okay?
Mhm.
So what we have here is we would have to consider his rate of pedaling. That's called the cadence, right? So maybe he's pedaling at 60 revolutions per minute. And would you agree the movement is a function of his pedaling, right?
Mhm.
The movement is also a function of how big these chain rings are and how big the tire is. So we have all these interconnected functions right here. And so it turns out the interconnected functions, the speed is just a product of their rates. So if you take the rate of change there, well, every time he makes a revolution, doesn't this thing move?
Mhm.
Yeah, let's suppose this has 52 teeth and this has 13 teeth. Usually there's a smaller one in back if you're looking for speed. 13 times 4 is 52. So every time this thing moves once, that thing moves 4 times. Okay, so 1 revolution in front is going to give me 4 revolutions in back. So that's the rate of change between this system right here. Right? And one's a function of the other, right? One makes the other act, right? That's functional. And then every time this moves, doesn't it make the tire move?
Mhm.
Yeah, so let's suppose this guy has 700 size tires, which is 700 millimeters, which would be, oh no, that's not right. It must be, what does 700 mean? I think that gives me 70 centimeters. Let's see, 70 centimeters would be right there. Yeah, that's about how big my tires are. So if there's 70 centimeter diameter in the tire, I need to know the circumference. So that means the radius is 35 centimeters. And the circumference is just, I could have just done pi times the diameter, huh? 70 pi. So that means every 1 revolution in back, oops, got in the wrong spot. That's just basic. Every 1 revolution in back is going to give me a distance of 700 pi centimeters. So what this is going to give me is revolutions in front, cancel revolutions in front, revolutions in back, cancel revolutions in back. And that chain of derivatives is what they are, is going to ultimately give me a speed in centimeters per minute of this bike moving along, which I can convert to miles per hour or whatever I want to do. Okay, so that's another example. We'll do some, which doesn't involve calculus, but it does involve functions, okay, and rates. All right, the bicycle chain rule. Next question was that picture one, which Sarah was 13, is that right?
Yep.
Okay, thank you. All right, let's do this picture one again. So I've got these two pictures to contend with. So let me screenshot those. And then we need a derivative. And I can't remember which function was which. The outer is g, the inner is h. So we have to, given that f of x is equal to g of h of x, we need to calculate what is f prime of x. So applying the chain rule here, the chain rule says take the derivative of the outer function, g prime, and multiply by the derivative of the inner function, h prime. Then we just have to keep in mind that g originally inside of it had that h of x. So that's what the chain rule says about this particular composition. And I think usually we're asked to evaluate this at 2. Is that true here? 4 this time. Okie doke. We'll do it at 4 then. So now we need to use this to figure out what is f prime of 4. So just substituting in what is g prime of h of 4, and then multiply by h prime of 4. And so we should be able to use the graph to figure that out. So let's see. H of 4, if I plug 4 in for h, I get out y equals 2. So that means I need to know what is g prime of 2. And I still have h prime of 4 to contend with. So g prime of 2 just says what's the slope when x is 2. And what does it look like the slope is there? Rise is up to right 2. Yeah. Yeah, so the slope here seems to be 1. So g prime of 2 is 1. And then if we plug in 4 into h, what does the slope appear to be right in this region? So what do we got? From here to here, down 1, right 2, negative 1/2, right? Minus 1. Yeah, so that'd be negative 1/2. So it looks like f prime of 4 is negative 1/2 according to the chain rule. So it's a matter of first figuring out what the chain rule tells us about this composition, and then backtracking and looking at the graphs to see if we can pull out the right numbers. So I think it's negative 1/2. All right. Other homework questions? Okay, so we're going to adopt a new section today. Derivatives of inverse functions. This is section 3.7, I believe. Yeah, so I'm going to review what inverse means, yes, and then we'll figure out how to do derivatives of inverse functions. So, yeah, inverse functions are functions that undo each other. Okay, so for example, let's say this is a parabola up there, so that red function, let's call that f of x, is x squared minus 1. To find an inverse function, ooh, plus 1, yes, sorry. Thank you. Good job. All right. To find an inverse function, it's a two-step process. You have to write it with just y's and x's is the recommended procedure. And these two steps are interchangeable. You have to solve for the other variable and switch the variables. And you can do those in either order you wish.
Why is it only showing one side of the parabola?
Because I chose to only show one side of the parabola.
So it isn't some sort of fundamental part of the equation of that?
No, I'm going to ignore that.
Okay.
Yeah. Yeah.
Okay.
And I guess I should explain that. If I'll explain that in a minute. So
Oh,
let
wait,
me
is
just
that,
do
is
this.
that the horizontal line test?
Yes, that is
Okay.
correct. Yeah.
Cool.
Yeah.
Okay, never mind.
So I will explain that though in a minute. So here I'm going to just solve for x first. So to solve for x, I would get rid of the 1. So then I get y minus 1 equals x squared. Next thing to do is to take the square root of both sides. So if I take the square root of both sides, I get y minus 1 equals the square root of x squared. Now there's 2 tricks on dealing with the square root of x squared. One trick is to say it's just an x and then put a plus or minus on the other side. The other trick is to call this the absolute value of x instead of the plus or minus. Either way is a problem for me because I just want an x. Okay? So let's suppose I go with the plus or minus route. Well, the plus would be this chunk right here. And guess what the minus would be? It would be underneath here, like that. Yeah. And the problem with the plus or the minus is this is now not a function. So I have to pick, choose plus or choose the minus. Okay. Well, since I only drew this side of the parabola, guess which side I want of the new one? I want the plus one. No, I want the top one. Yeah, and because they have to be mirror images about the line y equals x. So that means I'm going to chuck this one, so I'm going to get rid of the minus. So if I'm only focusing on that side of the parabola, that means my inverse would be just the positive square root, not the negative square root. Then you switch your variables. So switch x with y and vice versa. So now I get the square root of x minus 1, and that is what we call the inverse function. So that right there is f inverse, that's a negative 1 there, of x. Okay, which gives me a sideways parabola, which is a square root function in this case. So I'm going to clean up some of my mess here. So that's the process of finding an inverse function. And you may actually need to do that in some homework questions. Okay, so we could find the slope at this point right here if we wanted to, and we're going to get a tangent line. So let me whip out a tangent line there. So a tangent line, sure, let's go with black tangent lines, and let's make them dotted today or dashed. So like that-ish. Ooh, stop it.
No.
No.
A little off. That's a little better.
The hardest part.
Let's call that the tangent line right there. Okay. So just to check that, I already wrote what f of x is right here, true? So then f prime of x would be just 2x. And I'm plugging in x equals 2 there. So the slope there would be f prime of 2, which is 4 in this case. And so if I look at this, does it look roughly like it's going up 4 over 1?
Yes.
Yeah. Okay, to the best of my artistic ability, that's up 4 over 1. Well, bottom line with inverse functions, the big deal about those, highlighter, is switching x with y. Everything that was x becomes y, and everything that was y becomes x. Well, isn't slope change over y, change of y over change in x? So for the inverse function, I just need to swap that, okay? So f inverse of x prime is just going to take on change in x over change in y. So my claim then, the slope over here should be what? 1/4. If I evaluate that at x equals 2, I should get a 1/4 for the slope there. So if I go up 1 from there and over 1, 2, 3, 4, that'd be roughly over there. That should be the tangent line. So let's expand that sucker. And that looks pretty darn tangent, doesn't it? Yeah.
Does this have to do with like perpendicular lines?
No, perpendicular lines, their relationship is the negative reciprocal. So you flip it and you take the opposite. But if you look at like where the black line is about to intersect the red dotted line here, they definitely don't meet at a right angle, right? Yeah, so it's not perpendicular, although perpendicular does involve flipping, but it also involves taking the opposite. Yeah, so in this case, if the original function had a positive slope, the inverse will have a positive slope. So the signs will have to match, but we just flip the x and y stuff, okay? So I'm just gonna put that in a more general form now. So if we want to take the derivative with respect to x of some inverse function, well, that's just the reciprocal of the derivative of the original function. So that's inverse function there. Notice, because we put the primes here and we put the inverse symbol there, it gets very hard to put them together. So that's a little weird. So usually for notation, you'll see the derivative of the inverse function written like this. You'll also see it written like this, inverse parentheses prime. So you'll see the book use that notation, and people that write the online problems will often use that notation. But then there's some people like me that like that notation. Okay. But because these guys, they're competing for the same spot, we got to do one or the other. Now, here's the other thing. An inverse function undoes another function, right? So what I mean by that is if y equals f of x, then x has to equal f inverse of y. Okay.
Undo equals 1, undo equals 0.
What's that?
Does undo go back to 0, isn't it?
No, undo just means like cancel each other out. So for example, when I compose these together, now just note, what's the process of finding an inverse? There's a two-step process. First step is you solve for x. What's the second step in finding an inverse? You switch x and y. So then we rewrite that as y equals f inverse
And you can
of x.
do this in any order.
And you can do that in any order you want, correct? Yeah, you could switch those two. Yeah, you could switch them, but then you have to solve for y. Yeah, and you get the same answer. So when I do a composition here of functions, so if I take f and I plug in f inverse, what does this say f inverse is equal to? Y. Actually, I'm going to go back to the red version. What does this say f inverse is equal to? X. Oh, wait. This is not working out the way I want it to work out. What did I do wrong here?
Y.
Why is that not working out the way I wanted? If I then write f of...
Shouldn't it be y and then it goes x and then f of x?
That can't be right. Y. All right, I have a logical problem there I will resolve later and get back to you. But what happens is these guys cancel each other out. You're supposed to get x back. Okay, so in an actual example with real functions, if I say my original function was x squared plus 1, and then I replace x with the inverse function, then I'm going to get, what did we find the inverse function to be here? Square root of x minus 1. Okay, so square and the square root cancel each other. So then I get x minus 1 plus 1, which equals x. Okay. Yeah, but I get, the point here is that a function and its inverse cancel each other out. And I get x back. Okay. So I'm just going to apply this relationship up here. Actually, it's these two. X is the inverse function. So up here, what I get to say is f prime of, and instead of an x there, I'm going to throw in f inverse of x. Okay. And this is the formula for working with inverse functions. If you want to take the derivative of an inverse function, you can just flip the derivative of the real function, but then you stick inside of it the inverse function. I'm going to test that out. Okay. Before I do that, we have a couple of functions right here. So let's play with those first. So starting off with, uh-oh, my pen's freaking out. There we go. Starting off with, come on. There we go. F of x equals x squared minus 1. We claim f prime is, or f inverse is, sorry, the square root. Sorry, that's supposed to be a plus. There we go. And there's the minus. So f prime of x is, no, f prime. Yeah, f inverse is square root. F prime is just 2x. Okay. Now, just using the chain rule, what's f inverse prime? 1 over 2 square roots. And the derivative of x minus 1 is 1. So that's no big deal. So this is the derivative right here. Okay, so now we're going to apply our new fancy formula. The new fancy formula says if you have an inverse function and you want to take its derivative, then take 1 over the derivative of your function. It's inverse. The inverse of an inverse is the original function. So that would be 2 times something. But our formula said to plug in the inverse function there. So what's my inverse function? No, the inverse function?
F
Square root of x minus 1. Which,
the derivative that we got from the chain rule.
yeah.
Is there something wrong with
Wait, is it X
No, that's what I'm
minus
supposed to
or X
get.
plus one?
Yeah, these should match. That's supposed to be a minus. Sorry,
Can we
I
just
screwed
do
it
the
up.
chain rule, or does this not hold all?
Yeah, so the chain rule gives us the same thing as the inverse function rule in this case. So you'd say, well, who cares? I'll show you why we care in just a minute. So all I'm showing is that the formula works. So the formula says if you need to take the derivative of an inverse, take 1 over the derivative of your function, but then sneak inside of it whatever the inverse is. Sneak it inside.
So but it's always going to be 1/2 times 1 over the inverse.
If with a square root,
Okay.
only with a square root. Because notice the 2 pops up in both of them.
Yeah.
Because of the square and the square root. Yeah.
Okay.
Other functions are going to be different. Okay. So here's why we're going to need this. Consider f of x equals the sine of x. What's the inverse function? No,
Wait.
it's not cosine x. There's 2 ways to write the inverse function.
Oh.
One way would be sine inverse. Now, here's where we have to be super careful. That is not 1 over the sine.
Arcsine?
This is what's called the arc sign is the better way to write it. So I hate this notation. So
Arcsine.
Gary hates this, this notation. Yeah, because it leads people to want to flip the sign, which is not what I'm saying here. That's why I hate this notation. Yeah, the better terminology notation would be calling this the arc sine of x. On some computer systems, they just abbreviate that a sine, which that one bugs me a little bit, but it's common practice to write a sine. So this one is my preference right here, that we write it that way. So from now on, whenever I talk about the inverse sine, I'm never going to use this notation right there. Unfortunately, it pops up in the book, it pops up in the homework. I'm always going to call it arc sine, arc cosine, arc tangent, and so on. Okay. Well, what is the arc sine? Good question. I'm glad that you asked that. So if you consider the original sine, so just a quick review of some trigonometry. The original sine function is this nice wave that looks like this, roughly, and it goes back the other way, same way. If you tried to take the inverse of that immediately, right, you just switch x with y, then you get this thing that looks like this. That's not a function. Yeah, so what we have to do is we have to look at the sine function and say, okay, we have to chop this off. So not only does it pass the vertical line test, but it passes the horizontal line test. And the traditional way to do that is to cut it there and there. So then we consider just this chunk right here to be the sine. So between pi over 2 and negative pi over 2. If we do that, then the arc sine becomes this chunk of the wave there. Just that little piece right there. So if I plug this into a computer like Desmos, Desmos will only show me a chunk of this wave that would go up and down forever. But it can't because I need it to be a function. So if I go here and say, let's let g of x equal the, and I'm pretty sure it accepts arc sine. Yeah, it accepts arc sine of x. See, it just shows me that little chunk right there. And then if I want to know what those endpoints are, I don't know, will it show me the endpoints if I zoom in there? 1 pi over 2, and this one, guess what it is? Negative 1, negative pi over 2. Yeah, so it's just a flipped piece of the sine. How did they flip it? I'm glad you asked. So consider f of x equals the sine of x. The flip happens because we switch x and y. So if you look at the line y equals x and you zoom in there, you can see that these guys are mirror images about the line y equals x. Can you see that mirror image thing going on there? So that's that. All right, cool. Arc sine. Why do they call it the arc sine? Anybody know? What's that? There's an arc involved. Yeah, there totally is an arc involved. What the hell is the sine of x, or let's call it the sine of theta anyway? Well, the sine of theta, my favorite definition is on the unit circle. So this is a chunk of the unit circle. Here's some angle theta right there. If I'm on the unit circle, does anybody know how to measure the arc length there? It's theta. It's the same thing as theta. If it's not the unit circle, it's r times theta. Yeah, it's theta. So theta is an arc on the unit circle.
Like, so theta is 67 degrees. That would be 67.
Well, it's got to be in radians. It doesn't make sense in degrees.
There we go.
Yeah, so I talked about that yesterday in calculus. You've got to do things in radians for this to work. If you do it in degrees, all things are out. Yeah. So radians is basically a chunk of a radius, is what it is, thrown on the arc.
So to get
So here's the bottom line, though. What's the input of a sine? It is an arc. Why an arc? Because an arc is an angle. What's the output? The output is a ratio of whatever x to y is there. If I inverse this, then I'm calling it the arc sine, and the input is some ratio, x over y. The output is what?
Theta.
Is theta, and theta is an arc. So it's called the arc sine because it outputs arcs. That's why it's called the arc sine. Okay, so long story short, let's get busy and use it. We need to find the derivative of the sine. Inverse, the arc sine.
It's not just.
So what is, let's see, if we say g of x is the arc sine, what is g prime? Well, the technical definition for a derivative is to take the limit as h goes to 0 of the arc sine of x plus h minus the arc sine, oh, I'm running out of room, of h, who did it, all over h. Ruh-roh.
Oh dear.
Remember how hard it was to find the derivative of the sine?
Yeah.
We had to throw in a bunch of identities.
Yeah.
Yeah, identities for inverse functions are not as numerous and helpful.
Uh-huh.
So this right here is very troublesome. Not good. However, we have a new rule about inverse functions. Yes, Siler?
Isn't arc minus arc sine of x
Oh, that should be an X there. Yes, thank you. I messed up there. Good job. That is an X. Yeah.
It was so
Yeah.
It was so helpful that said
So that was, yeah. So with the H there, it's even more troublesome. Very, very troublesome. Now that it's written correctly, it's only very troublesome. So we have the inverse function theorem is what we're going to apply here. So, so here we're going to say f of x equals the sine of x, and f inverse of x is equal to the arc sine of x. Okay, so the what's f prime?
Cosine.
It's just the cosine of x. Okay, so the inverse function theorem, switch back to blue, says that if you want to take the derivative of an inverse function, then just consider the original function and look at 1 over its derivative. So that means I want 1 over the cosine. But the catch is I have to put something else inside there. What am I going to throw in there instead of an x?
Arcsine.
Yeah, it's the inverse function gets thrown in there. So again, the derivative says take 1 over f prime of f inverse of x is what it says.
Would it be arcsine or arccosine?
F inverse is arc sine. Yeah, so inside the cosine, I have to stick the arc sine.
And that's the derivative.
That's the derivative. Now, that cosine of the arc sine, you solved problems like that way back in trigonometry when you first got introduced to these inverse functions. So we're going to try and do that right now. So we're going to simplify this. And we're going to have to go back to some basic definitions of trigonometry to do that. So, what is the arc sine? Okay, but it is the inverse sine, but more basically, what is it? It's an arc or an angle. Okay, what do we usually refer to an angle with? Usually we refer to it as a theta. Okay, so first step, rewrite arc sine as an angle, call it theta. What does that look like in a triangle? Well, if I rewrite that right there, that says that x is equal to the sine of theta. Triangle, if I draw a triangle here, here's theta. What's the definition of sine on a triangle? Opposite over hypotenuse. So I'm going to view that as x over 1. So the opposite is x here, and 1 is the hypotenuse. Okay. How do I figure out what the adjacent side is then?
Cosine.
Okay, without using cosine.
Or
I have to use the Pythagorean theorem.
Yeah.
Right? Pythagorean theorem says that, I guess I'll call it A for adjacent maybe. Yeah, it's going to be almost. So if I call that A,
x squared minus 1.
A squared plus x squared equals 1. Solving this for A, I get A squared equals 1 minus x squared, and then take the square root. A is the square root of 1 minus x squared. So my adjacent side is really the square root of 1 minus x squared. Okay, so here's where I'm at. I realize the arc sine is really an angle, so I write it that way and turn it into a triangle. Next, I'm trying to clean up, oops, wrong letter, the cosine of the arc sine of x. What is the arc sine again?
The angle.
It's an angle. So I can say that this black statement right there is really just the cosine of theta. Based on this triangle, what is the cosine of theta?
1 minus x squared.
It is the square root of 1 minus x squared, because the cosine of this theta is adjacent over hypotenuse. So we have just determined that the cosine of the arc sine of x is equal to the square root of 1 minus x squared. So what is the derivative with respect to x of the arcsine of X. Well, if we look back at our previous page, we were stuck at 1 over the cosine of the arcsine. But now we know the cosine of the arcsine is really square root. Yeah, so now we know that this derivative is 1 over the square root of 1 minus x squared. That's the derivative. I know. That's whack, yeah.
So how we use this in everyday life again? It's the applied.
Yeah.
Because I'm getting confused.
So applications, bottom line is there's lots of periodic motion in the universe. That means you need sines and cosines to describe that periodic motion. Anytime you have periodic motion, you need to figure out how to describe it, to undo it, and to look at how it's changing. So not only do we need to know how the periodic motion is changing, but we also need to know how the angles are changing in that periodic motion. So this is the derivative of how the angle is changing. Yeah. So bottom line is anytime periodic motion is involved, you need sines and cosines, you need inverse sines and cosines, and you need derivatives. So now we've nailed all 4 of those. So can we describe anything related to periodic motion? Yeah. There's some problems that are wicked hard, and then we have to whip out a computer, right? But this gives us the basic. Rob, were you stretching? Dylan, were you stretching? You had a question. Okay. All right. So guess what we need next? Derivative of arctangent, derivative of arc cosine.
Are you just gonna give them to us?
6 minutes.
Gary, don't think about this.
We're gonna do one more. Let's go. We can do another
And
one.
this isn't always
You always say we can do another
the
one.
derivative
Yeah.
of.
So we're gonna find the derivative with respect to x of the arctangent.
Is this an always for the arc sine?
Yes, always.
Since we're not using any actual numbers.
Yeah.
I
So
didn't know this.
since Sarah wants some kind of always thing, then I'm gonna combine that with the chain rule. So if we take the derivative with respect to x of the arc sine of some u, where u is a function of x, then we're going to get 1 over the square root of 1 minus u squared times u prime.
Okay.
So in action, if we had to take, let's see, a different color, if we had to take the derivative with respect to x of the arc sine of 3x minus 7, then we're going to get 1 over the square root of 1 minus, parentheses, 3x minus 7 squared times the derivative of 3x minus 7, which is 3, which cleans up to be just 3 over the square root. Yeah, so now that we have the chain rule, derivative formulas are often going to be stated with the chain rule involved if you have something extra. If that was just an x, x prime would be the derivative of x with respect to x, which is just 1. Doesn't change much. All right. So we have enough time to set up, but probably not finish the tangent. Let's give it a try. Uh-oh, what happened there? Oh, nope. There we go. So we're going to apply the inverse function theorem, which says if you take the derivative with respect to x of an inverse function, I'm just going to write the general thing. Oh, sorry about that. Hi. We have another class that's not over yet. So yeah, we'll just be a minute. Then that's going to be 1 over f, the inverse of the inverse, with the f prime, sorry, with the inverse plugged in. All right, so applying that here, what's the inverse of the tangent? Sorry, the arctangent?
Tangent.
Leave it away. It's the tangent. What's the derivative of the tangent?
Secant X.
secant squared. Okay. But the theorem here says I need to plug in the arctangent. That's one version of the derivative. Do you think we can clean it up a little bit?
Probably.
Yes, we can. So we're going to do that. And I think I can squeeze that right in here. So an arc function is really an arc or an angle. So I just draw a picture of what that looks like. That means I need to consider the tangent of theta equals x, because there's an x here. So drawing that out, if this is theta right there, tangent is opposite over adjacent, right? So the opposite is x, the adjacent is 1. And then over here, I'm going to get the square root of x squared plus 1. Now I need to know, based on this picture, what is the secant of theta? Well, secant is what? 1 over cosine? So cosine would normally be adjacent over hypotenuse. So the secant is going to be hypotenuse over adjacent. So the secant is just going to be the square root of x squared plus 1 in this picture. And what do I get to do with it next? Square it. So I lose the square root. So the derivative here must just be 1 over x squared plus 1. Okay.
And that's an always for arc.
That's an always. Bottom line.
Don't laugh. The less I have to memorize, the better.
Yes. So this is the derivative of the arctangent. 1 over x squared plus 1.
I need to make a list of all the.
Yeah, we'll make a list of those next class.
And
Or you could do it this weekend.
The chain rule applies.
The chain rule would, yeah, so if we had something like the derivative with respect to x of the arctangent of u, then it's going to end up being u prime over 1 plus u squared.
So have we technically just been applying the chain rule this whole time, because it's always just been x inside of the thing and the derivative of x is just 1, so it doesn't mean anything?
Yes.
I don't like that.
Yeah, technically the chain rule has always been acting in the background secretly.
Gary, can you tell X to solve its own problems?
Yeah.